This is Mr. Alexander, and I'm here to talk to you today about our notes over inverses, and hopefully by the end of these videos you will have three major takeaways, which I will address as we find them. First one here is we're trying to find the inverse of this cubic function x cubed plus 4. In order to do that, I need to first fill in a table here that has the x's and y's of the cubic function. So the easiest way to fill in a table like this is just go to the calculator, go to y equals, type in x math 3 for x cubed plus 4. And I'm going to go second graph, and I'm going to get a table of values here. So I've got -2, -4, -1, 3, 0, 4, 1, 5, 2, 12, 3, 31, and 4, 68. Now the first major takeaway about inverses that I want you to take with you after this video is that to find the inverse, you simply flip the x and the y. So -2, -4, that becomes -4, -2. 3, -1 becomes, or -1, 3 becomes 3, -1. This is 4, 0, 5, 1, 12, 2, 31, 3, and 68, 4. So first major takeaway, you've got a function. To find the points that define the inverse, just flip the x and the y. I'm going to do the same thing here. I'm going to type in x minus 1 squared, and I'm going to go second graph. I'm going to do -2, 9, -1, 4, 0, 1, 1, 0, 2, 1, 3, 4, 4, 9. So to find the inverse, I'm just going to flip those x's and y's. Make it 9, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, 3, 9, 4. So if I was to summarize the first major takeaway, I'd summarize it by saying we can conclude that the inverse of a function can be found by exchanging the independent and dependent variables, i.e. switch the x and the y. That's the first major takeaway. So what I'm going to do is I'm going to use this table of values I've just created to graph the original function and the inverse and the line of symmetry, which we haven't talked about yet. But I'll be using this table right here to graph this function. So let me just zoom out a little bit so you can see it, the table and the graph here. I'm going to plot the point -2, -4, 3, 4, and the point -1, 3, 0, 4, 1, 5, and the rest of these points won't fit on the graph. Now, I know this is a cubic function because it's y equals x cubed plus 4, and I know that a cubic function kind of has that wiggle characteristic to it, so I'm just going to try and graph that little wiggle thing that's going on there. That's what the cubic looks like. I'm going to label that as f of x, the original function. Now in a different color, I'm going to use orange. I'm going to graph the inverse here. So I've got -4, -2, 3, -1, 4, 0, 5, 1, and that's all I'm going to get. So I've kind of got this wiggle action going on again, but it's kind of at a different angle. I'm going to label that the inverse. So you look at these graphs and hopefully you see something interesting going on here. They're very similar looking. It's just kind of like it's been rotated. Like I took this black function and I rotated it. What I actually did was I reflected it. It's a reflection over here. The question is, what's it a reflection over? And it turns out that it's a reflection over the line y equals x, which is our second major takeaway. Two functions are inverses if they are reflections across the line y equals x. I'm going to go ahead and graph that line y equals x. And it's just a straight line. You only need 2 points to define a line, so I'm going to graph 2 points. And I'm just going to use a straight edge to draw in this 45-degree line here. Now, if I've done it correctly, the place where these graphs intersect, they should intersect right on that line y equals x. I'm going to do the same thing over here, and using the information we just had, it should be pretty clear what's going to happen. But let's just summarize the first two major takeaways before I go ahead and graph those. So the first one is to find the inverse, flip the x and the y, and then once you found the x and the y, once you found that table of values, you can tell that they're inverses if they are reflections across the line y equals x. If it doesn't look like a reflection across the line y equals x, they're probably not inverses. Alright, so let's go ahead and graph this one now. I've got the table of values. I'm not going to zoom out. I want you to actually see what I'm doing here. So I've got negative 2, 9 is my first point for the original function, x minus 1 squared. I've got negative 1, 4. 1, 2, 3, 4. I've got 0, 1. I've got 1, 0. I've got 2, 1, 3, 4, and 4, 9. This is my original function. It's a parabola, which means it's a quadratic. Alright, now, in my other color, I'm going to use orange. I'm going to graph the inverse. So the first point I've got is 9, negative 2. And I've got 4, negative 1. I've got 1, 0, 0, 1, 1, 2, 4, 3, and 9, 4. I'm going to draw in this parabola, which has been flipped on its side here. That's my inverse. And this one's my original function, f of x. Now I'm also going to do that line of symmetry, y equals x, to make sure that it looks like it's supposed to look like. It should be a reflection across this line, y equals x. If I've done it correctly, then the places where these two graphs intersect, they will intersect along the line y equals x, which appears to be the case. It happens like right in there and right there. So it looks like it's doing what it's supposed to be doing. So this looks right. It looks like a reflection across the line y equals x. Let's talk about domain and range for a second here. So I've got this function. Let's look at this cubic function right here. And I'm trying to figure out the domain. There's a bunch of different ways to think about the domain, but my favorite is simply to think about how far left, how far right. So how far to the left is this thing going to go? It's going down forever. That's pretty clear to see. But it's also going to be going to the left forever. When that happens, and it goes to the right forever, we say that's the domain of all real numbers. Now that shouldn't be unexpected, because when we were studying cubics last semester, we said that the domain of all cubic functions was all real numbers. The same is true for the range. The domain and range for cubic functions is all real numbers. Now the inverse, this thing's clearly going to the left forever, clearly going to the right forever. That's also all real numbers. The range, how low to how high, this thing's going to slope down forever and slope up forever. So the range is also all real numbers. Now I said there are 3 takeaways, and we've already talked about 2 of those takeaways. The third takeaway we're about to do right now. It's going to happen. Some magic's going to happen here. You'll see. The original function, the domain, this thing goes to the left forever, it goes to the right forever. The domain is all real numbers of the original function. The range, however, how low to how high, the lowest y value is 0. The highest y value is infinity. Now I'm going to use interval notation. You use a square bracket when it actually touches that point, so it actually touches 0. It approaches infinity but never quite gets there. Therefore, we use a parentheses there. Now let's look at the orange inverse here. The domain. How far left, how far right? Well, the furthest left it goes is to this point 0 right here. So it's going from 0 to infinity. But the range, going down forever, and up forever, so the range is all real numbers. All right, here it is. Here's the third major takeaway. If a function is an inverse of another function, these two things are inverses. When two things are inverses, you can just exchange the domain and range. So the domain of the original becomes the range of the inverse, and the range of the original becomes the domain of the inverse. The same thing was happening over here. You just couldn't see it because they were both all real numbers, but it's pretty clear here what's happening. The range becomes the domain of the inverse, the domain becomes the range of the inverse. That's the third major takeaway. All right, I'm going to turn over the page now, and it's going to ask you a question. I'm going to have to flip back. It says, is the inverse of x cubed plus 4 a function? So is this this orange thing right here, is this inverse a function? Is it an inverse function? The answer is yes, because it's going to pass the vertical line test. Remember, the vertical line test is, as I run a vertical line across this orange function here, do I ever touch more than one point at a time? No, I do not. So yes, it is a function because it passes the vertical line test. And I'm going to go ahead and abbreviate that VLT for vertical line test. I think we can all understand what that means. But this is the next one. Is the inverse of x minus 1 squared a function? So I'm looking at that thing, and I'm running it. Oh, look right there. Vertical line test. It fails because right there I'm touching 2 points. So no, it's not a function. But here's the real question. Is there something I could do to the original function? Is there something I could do to x minus 1 squared such that the inverse becomes a function? And this is where we get talking about things called domain restrictions. Imagine I just took this parabola and I split it in half. I said, hey, I only want that part of the parabola. Well, when I graph the inverse, the top part of the inverse drops out, and all I have is the bottom part of the parabola. And you know what? That is a function right there. Now I could do something similar. I could say, well, instead of getting rid of this part, the right-hand side of the parabola, let's get rid of the left-hand side. Let's cover that up. When I do that, then it gets rid of the bottom part of the inverse here. And hey, you know what? That is a function as well. So the question is, how do I split this thing in half? Well, I hope you agree that this line, this dotted line I just graphed right there, that's x equals 1. That's the line that splits that parabola right in half. So the inverse is not a function unless the domain of f of x is restricted. Question is, what do I restrict it to? Well, I want to split it in half. So it's either going to be from negative infinity to 1, or it's going to be from 1 to infinity. It doesn't matter which half you take, as long as you only take half of the parabola, the inverse becomes a function. Because then you just have the half of the inverse there. So the question is, what's the domain restriction? Well, you can either restrict it from negative infinity to 1, cut it in half that way, or you can cut it in half the other way by restricting it from 1 to positive infinity. So that's the only way to turn the inverse of this into a function, is by restricting the domain. All right, I've got some other things I need to talk about. We need to talk about how to rewrite equations such that we can find the inverses of the equations algebraically. I'm going to have to do that on a second video because I've run out of time. So to watch the remainder of these notes, please refer to the next video. All right, we'll see you in just a moment.